Hello, my friend. Welcome back to You Can Do TV channel. There are loads so large that preparing to lift them becomes a project of its own. Right from the opening images, the number is enough to break ordinary intuition. More than 24,000 tons. At that scale, this is no longer just a heavy object hanging from steel. It is a rigging system where every sling angle, every connection point, and every load path has to behave exactly as intended. One bad assumption can change the character of the whole lift. That is the first shift that matters here. Once the load moves into this range, weight stops being something people feel and becomes something engineers manage. The question is no longer whether it can be lifted at all. The real question is whether it can be lifted in a way that remains stable, predictable, and controlled from the first inch to the last. And that is what makes a scene like this so striking. The impressive part is not just that the number is enormous. The impressive part is that a load this extreme can still be handled through geometry, sequence, and control rather than brute force alone. Once the load moves beyond what ordinary crane work can handle efficiently, systems like this begin to make sense. One number says almost everything. About 1,409 tons at a 328-foot radius. That is not just a power figure. It is a statement about control at distance. Because the farther the load moves from the center of the machine, the harder the machine has to work simply to preserve its own balance. That is what people often miss when they first see super heavy lift equipment. The hard part is not always lifting more. Sometimes the hard part is lifting far enough, high enough, or cleanly enough to make the move possible at all. A giant component may be heavy, but it may also be tall, awkward, wind-sensitive, or difficult to guide into position. So what looks like oversized strength is really something more specific. It is a machine built for jobs where weight, reach, and stability all become difficult at the same time. The more closely a configuration like this is watched, the clearer one thing becomes. The hardest part is not the hook. The load is out front, the boom is overhead. But behind that visible picture is the real fight for balance. Counterweight, support geometry, and force distribution are all working together to keep the system from tipping into instability. That is why a major lift is rarely the story of one machine acting alone. More often, it is the story of several force systems being made to behave like one. One part carries, Another stabilizes. Another offsets the overturning force building somewhere else. And that is a useful way to watch everything that follows, not as a parade of giant machines, but as a study in controlled balance. At this scale, capacity by itself is never enough. What matters is whether the entire system can hold its geometry while the load is moving. Then the focus comes back to a machine that looks more familiar, the Liebherr LTM 1650-8.1. At first glance, it still reads like a road-going crane, but that familiarity is deceptive. This is an 8-axle machine carrying a 177-foot telescopic boom, powered by about 686 horsepower and working in the 700-ton class. Even the mobile side of heavy lifting is already operating far beyond ordinary job site logic. And that is where the deeper question begins. A crane does not carry one fixed load under all conditions. Its real capacity depends on working radius, configuration, counterweight, and the ground beneath it. Move the load farther from the center of rotation, and more of the machine's strength is spent preserving balance rather than lifting useful weight. That is why the biggest cranes cannot be understood by headline capacity alone. The number matters, but the conditions matter more. So by the end of this opening section, the real subject is no longer just scale, it is control. These machines exist because some loads are so large, so awkward, and so demanding that lifting them safely becomes a systems problem. And that leads directly to the next question. What kinds of lifting systems do humans use when the load is almost too large to move at all? And why does each one exist in the first place? The first real answer begins with a machine that looks more familiar than the extreme systems from the opening. The Liebherr LTM 11200. At first glance, it still reads like a road-going crane, but that impression does not last once the setup begins. A machine like this does not arrive ready for its hardest work. It arrives as a mobile base, and then piece by piece, it has to be transformed into the version of itself that can actually take the job. The boom sections arrive. The telescopic assembly is connected. Counterweight starts going on. The hook system is installed. Support gear is added. Step by step, the machine is moving from transport logic to lifting logic. The numbers explain why that transformation matters. In the configuration shown here, the counterweight is about 135 tons, and it can be taken up to roughly 223 tons. Those are not just impressive figures. They tell you that the crane's real identity depends on what has been added to it, how it has been configured, and what problem it is being asked to solve. That is the first major lesson here. A heavy mobile crane is not one fixed machine in practice. It is a platform that can be built into different working forms. Every added section changes what it can reach. Every added counterweight changes what it can resist. None of those steps are cosmetic. They are structural. And that is why the earliest hours on a site like this matters so much, even though they can look uneventful from the outside. Nothing dramatic is being lifted yet, but the conditions for the real lift are being built. The crane is being given its operating shape, its balance envelope, and its safe working logic. The hook height on screen is a little over 340 feet, and with the larger setup, it can approach 656 feet.
That also explains why mobile heavy lifting is more demanding than it appears. The machine has the advantage of getting to the site under its own transport logic. But once it arrives, that convenience largely disappears. Now it has to be rebuilt into a stable lifting system, and that process has to happen in the right order. Because with a crane this large, order is not a formality, it is what makes the final lift possible.
Then the logic gets more interesting. This sequence of the LR 1600 halves using an LTR 1220 as counterweight reveals something people outside the lifting world rarely stop to think about. Sometimes the real engineering story is not in the load itself. It is in what keeps the crane from becoming unstable while the load is moving. That is what counterweight really is at this level, not spare mass, not a stack of steel for its own sake. It is part of the machine's ability to exist in a working condition. As the load moves farther from the crane centerline, the overturning force increases. That means the backside of the system has to answer it. And answering it efficiently is not always about bringing in more dead ballast from somewhere else. Sometimes the better solution is to use the available mass of another machine as part of the balance strategy. That is why this approach matters. It cuts ballast handling on site, reduces transport burden, and turns existing mass into a functional part of the lifting geometry. In other words, it is not just strong, it is efficient in the engineering sense. It reduces unnecessary movement while preserving the stability the lift actually needs. And that points to something larger. Heavy lift design is rarely about solving problems with force alone. More often, it is about reducing how much force the system has to waste. Better balance means less strain. Better sequence means less exposure. Better geometry means more useful capacity. So even in a short sequence like this, the deeper logic is visible. With the LG 1750, the picture changes again. This no longer feels like a mobile crane being outfitted for a larger task. It begins to feel like a structure being erected in its own right. Access roads have to be prepared. The site has to accept incoming truckloads of components. Space has to exist not just for the crane's final footprint, but for the assembly process that leads to it. That difference matters. Once lifting systems reach this scale, they stop behaving like self-contained equipment. They start behaving more like field-built systems. Major elements arrive separately. They are staged separately. They are installed separately. And only after that does the full machine begin to exist in a meaningful operating sense. That is one of the hardest things for a casual viewer to see, because what reads as one crane is often really a temporary convergence of many parts, many deliveries, and many setup decisions. The machine in working form is not what came through the gate. The machine in working form is what the site gradually creates. That is why the setup phase deserves so much attention. It is not just a prelude before the interesting part. At this scale, setup is part of the lift. The route matters because the machine arrives in pieces. The laydown area matters because those pieces need order before they can become structure. The ground matters because every stage of assembly creates a different temporary condition, and each condition has to remain stable before the next one begins.
The larger the lifting system becomes, the less useful it is to think of it as a product, and the more useful it is to think of it as a process.
The next LG1750 sequence makes that even clearer, because now its final scale is easier to read. The height shown here reaches about 456 feet, with a rated capacity around 827 tons. Those are powerful numbers on their own, but the more revealing story is how the machine gets there. The most impressive thing is not simply that it becomes tall. It is that it can move from a collection of components to a structure this large without losing control during the intermediate states. And those intermediate states are where much of the real risk lives. Once a heavy crane is fully built, its geometry is clearer and its behavior more predictable. But in the middle of assembly, the system is still changing. One piece is installed, another is not. One structural path is complete, another is still open. The machine has not yet become the final version of itself, but it still has to stand safely long enough to get there. That is why sequence matters so much in lifting work. Sequence is not just about efficiency, it is about survivability. Install something too early, and a temporary condition may be created that the rest of the system cannot safely support yet. Install something too late, and the crane may not be ready for the next controlled move. Even the timing of when weight is added or when geometry changes matters, because each change reshapes the forces moving through the structure and down into the ground. This is also why large lifting systems often look calm on screen, even when the underlying work is highly demanding. The calmness is the point. If the sequence is right, each step arrives in a condition the system can safely accept. That is what professional setup looks like. It does not advertise the instability that was avoided. It simply never lets that instability happen in the first place. And that is one of the clearest signs of competence in heavy lifting. Not how dramatic the move looks, but how little the site seems to be improvising while it happens.
Then the scale shifts. The Potain MC85B does not belong to the same class as the giant cranes already seen, but the underlying logic is easier to read here. A tower crane begins at the base, then grows section by section. Each new piece depends on the one below it, and the structure only becomes reliable by passing through each stage in the right order. That is what makes a sequence like this so revealing. The crane does not appear all at once. It is built into existence. One section goes in, then the next, and every step has to leave the structure stable enough to accept the next move safely. That pattern is not unique to tower cranes. It runs through the whole lifting world. Before a crane can perform work safely, it often has to be assembled into a condition that can support its own next stage of growth. People usually think of cranes as the machines that assemble everything else. And they do. But first, the crane itself may have to be assembled through a careful series of lifts, placements, and lock-ins. In that sense, the crane is both the builder and something that must be built. You can also see why temporary conditions matter so much. A completed tower crane has a clearer structure and more predictable behavior. But while sections are still being added, the system is in transition. It is partly complete, partly incomplete, and still responsible for holding the next step safely. That is why setup work rarely looks dramatic when it is done well. The goal is not to create tension, the goal is to remove it before it has a chance to appear. And the same principle carries across every machine seen so far. Whether it is a road-going LTM 11200, a crawler-based LR 16000 halves, a large LG 1750, or a tower crane like the Potain MC85B, the pattern stays the same. The crane that arrives is not yet the crane that lifts. Between those two states, a great deal has to happen. The base has to be ready. The parts have to be staged. The order has to make sense. The support conditions have to hold. And the machine has to remain safe not only in its final form, but in every unfinished form along the way. That is where the real sophistication begins to show. Heavy lifting is not only about controlling a giant load once the hook is attached. It is about controlling everything that has to happen before that moment becomes possible. And once the crane is finally ready, the next question becomes harder still. Where will the load actually travel? How will the site carry the forces back into the round? What path does the component follow from arrival to placement? And why do so many of the biggest lifts, which look brief from a distance, really depend on an entire site already arranged around them? Act 3. The lift does not happen at the hook. It happens across the whole site.
The lift begins long before the crane ever takes the load. In offshore wind, the parts arrive already pushing the limits of transport logic. One tripod weighs about 650 tons. One upright tower section comes in around 234 tons. Even the nacelle is roughly 386 tons. At that scale, the hard part is not just lifting, it is getting each piece to the handoff point in the right orientation on the right transport system with enough clearance to make the next move clean. A bad approach path can turn a manageable lift into a slow and expensive problem.
That is why yard moves matter so much. On paper, this reel move may look simpler than a turbine installation. In reality, it reveals the same engineering logic in a form that is easier to read. The reel itself is about 37 feet in diameter, a little over 17 feet wide, and weighs roughly 419 tons. The fully rigged Terex Demag CC2500-1 being moved on site comes in at about 567 tons, spread over a 24-axle transporter with a 157-foot main boom. Those numbers tell the story. This is no longer about whether one machine is strong enough. It is about how the load travels through the whole site. The route has to be wide enough. The ground has to accept the axle loading. The turning radius has to work before the move begins, not after. And the crane has to arrive in a position that makes the actual lift safer, shorter, and more predictable. That is what heavy lifting often looks like when it is done well. The dramatic moment is brief. The real skill is built into the setup. A great deal of risk is removed before the hook ever takes weight. At this scale, moving a load a few feet in the wrong sequence can create a problem that no amount of horsepower fixes later. Now the problem gets harder. A 3,000 metric ton offshore mast crane means a little over 3,300 tons of lifting capacity, or about 6.6 million pounds. But the real difficulty is not just the number. It is the fact that this system lives on a vessel, not on a fixed pad. So the crane, the deck, the ballast, the load path, and the sea state all become part of the same equation. On land, gravity and geometry dominate the job. Offshore, those still matter, but now the working platform itself is never quite the same as solid ground. That is why installing and commissioning the crane matters so much. Before it can lift jackets, monopiles, or wind components, it has to be erected, integrated, tested, and trusted as part of the vessel. Even the timeline stands out. The onboard installation, commissioning, and testing of this 3,000 metric ton Huisman crane was completed in 27 days. That sounds fast because it is fast. What makes it possible is not rushing, it is sequence. Each step has to leave the system stable enough to accept the next one. And that pattern keeps coming back. The biggest moves are usually built on a chain of smaller moves, each one designed to make the next step safer and more controlled. Then the problem changes again. The claw was not built just to lift heavy objects. It was built to recover damaged offshore topsides from the seafloor, with less diver exposure and less stress on already fragile structures. Each of the two grappling units stands about 122 feet tall, spans roughly 112 feet, and weighs about 1,000 tons. Those are enormous numbers, but the real challenge is precision under bad conditions. A salvage lift is harder than a clean installation because the load may be distorted, weakened, or resting in an awkward position. This is not a new component designed to be lifted. It is something damaged, unstable, and difficult to approach. So the engineering value here is not just brute force, it is controlled recovery. The system has to grab, support, and transfer the load without turning a difficult retrieval into a collapse.
By the time the river reaches Yusufeli, the setting itself becomes part of the problem. The challenge here is not just a big lift. It is a big lift in terrain that refuses to make anything easy. On a wide, flat site, heavy equipment can often be staged, repositioned, and fed into the sequence one step at a time. In steep country, that freedom begins to disappear. Access narrows, working room shrinks, and ordinary delivery methods stop being ordinary. That is why scenes like this feel so striking. A concrete mixer truck, a machine people usually think of as routine, suddenly has to be treated like suspended cargo. The machine has not changed, the site has, and that changes the whole method. This is where heavy lifting stops looking like a machine problem and starts looking like a systems problem. The crane is only one part of it. There also has to be a route, a drop point, a receiving area. Timing, communication, and enough confidence in the sequence to know that once the load leaves one safe condition, it can reach the next one without losing control in between. That is what difficult terrain does. It exposes whether the plan was real or whether it only looked good on paper. And that is why lifts like this matter beyond the spectacle. They make construction possible in places where conventional access, conventional placement, and conventional workflow begin to break down. When the terrain removes the easy method, lifting becomes the method. Act 4. What is waiting on the other side of those lifts?
By this point, the larger picture begins to take shape. Heavy lift systems do not exist in isolation. They exist because modern industry keeps producing machines that are too large, too heavy, and too awkward to fit inside ordinary transport logic. The Bell Law's 75,710 is a perfect example. It carries almost 500 short tons, stretches about 67.5 feet long, and measures roughly 33.5 feet across at the front. It uses two 2,330 horsepower diesel engines, feeding an electric drive system through 4 traction motors. That is not just a big truck. It is a machine built at a scale where powertrain architecture, tire loading, steering geometry, and structural packaging all become part of the same extreme design problem. And that is why equipment like this belongs in the picture. It shows the industrial world waiting at the far end of heavy logistics. The giant crane, the transporter, the prepared route, and the rigging plan all make more sense once the machines they serve are seen clearly. Because once equipment grows to this scale, nothing about it is ordinary anymore. It cannot simply be shipped whole, it cannot be repositioned casually, and it cannot be supported by ordinary maintenance thinking. The machine itself becomes a long-term logistics problem even after it enters service.
Then, the scale shifts again, and the truck is no longer the biggest thing in the frame. Bagger 258 weighs about 4,240 tons. It stretches roughly 561 feet from end to end, stands around 164 feet tall, and delivers about 7,450 horsepower of drive power. Even the bucket wheel itself is about 49 feet in diameter. Those numbers sound exaggerated until the machine is seen against the landscape. Then the real point becomes obvious. This is not equipment designed to work inside a site. It is equipment designed to reshape the site itself. That changes the meaning of heavy lift all over again. A machine like this does not just need components, it needs infrastructure around it. It needs roads, power, maintenance planning, and transport logic capable of feeding something that operates on the scale of a moving industrial structure rather than a conventional vehicle. And that ties directly back to everything earlier. The giant lift is not the end of the story. It is one stage in a much longer chain. A turbine section, a crane component, a mining structure, or a replacement assembly only gets lifted because somewhere beyond the lift there's a machine, a plant, or a production system waiting for it. Then the picture briefly drops from the spectacular to the practical, and that contrast matters. The Volvo EC700CL is far smaller than the machines around it, yet it still weighs about 85 tons. It carries a 66-foot long-reach setup, works benches between roughly 23 and 30 feet high, and supports a site expecting around 441,000 tons of aggregate output per year. That is a useful reminder. Not every important machine in this world needs to look impossible. Some matter because they keep material moving every day. That brings the story back to a crucial idea. Even the machines that do the work often have to arrive as a project before they can become a machine. The Hitachi EX 1900-6 is shown being assembled from separate shipped components. That detail matters more than it may seem at first. Once a machine reaches this size class, it stops behaving like a self-contained product. It becomes something closer to a field-built system. Major structures travel separately. Large assemblies have to be joined on site. and the clock starts running long before the first bucket touches material. This is the same pattern seen with the cranes themselves. Large machines often cannot arrive in working form. They have to be broken down to move, then rebuilt to operate. That means the industrial world on the far side of heavy lifting still depends on heavy lifting just to come into existence. So by the time a shovel, a truck, or a giant excavator finally goes to work, the real story has already begun much earlier. It began with transport limits. It passed through assembly. It passed through lifting, and only then did it become production. That is what makes this industrial landscape feel so different from ordinary construction equipment. Nothing begins simple, nothing moves casually, and nothing at this scale exists without a long chain of hidden preparation beneath it. By now, one thing should be clear. Giant lifting systems do not exist only to assemble new projects. They also exist because the machines at the center of mining and heavy industry are too large, too valuable, and too difficult to replace casually. This overhaul of a CAT 7945 electric rope shovel makes that point perfectly. The rebuild takes place after 100,000 operating hours. It required more than 24,000 labor hours in the mine and more than 4 months of work. Some of the major structures are listed at up to 99 tons, with boom components around 77 tons and about 69 feet long. Even frame sections come in at roughly 39 feet long and 66 tons. Those numbers explain why work like this matters. A machine of this scale is not treated like equipment that simply gets retired when it wears down. It is treated more like industrial capital that can be taken apart, renewed, and returned to service. That changes the meaning of heavy lift once again. The crane is no longer just helping construction move forward, it is helping industrial life continue. And there is something else this sequence makes clear. The hardest part is not simply lifting the biggest piece. It is controlling the order of removal and return. One component comes off so another can be reached. One structure returns only after the supporting systems are ready. The machine is being dismantled and rebuilt as a layered system, not as a pile of unrelated parts. Scale alone does not explain why these jobs are difficult. What makes them difficult is that every large piece belongs to a larger machine, and that larger machine only works when its geometry, clearances, and structural relationships return in the correct order. A rebuild at this level is really a controlled reversal of assembly, followed by a controlled replay of it.
So the real takeaway is not just that the shovel is huge, it is that equipment this large creates its own maintenance economy. It needs specialized labor, specialized rigging, specialized staging, and specialized planning simply to remain part of daily production.
The same logic appears again with the CAT D11R, even though the machine feels more familiar and less exotic than a giant shovel. A rebuild like this makes a simple point. In heavy industry, the machine that keeps working is often more valuable than the machine that merely looks impressive. The dozer is stripped down to the frame and rebuilt back into working condition. That alone says a great deal about how this world thinks about equipment. Large machines are not disposable. They are platforms that can be restored, renewed, and sent back into the field. And that idea fits perfectly with everything that came earlier. The giant crane, the transporter, the rigging plan, and the site move all belong to an industrial culture built around control. Not only control during the lift, but control across the full life of the machine. Then the scale changes again, but the logic does not. A 4-ton tire weighs about 8,000 pounds. That is not something handled casually. It is a reminder that in the mining world, even maintenance items can weigh as much as a large pickup truck. That matters because tires sit where all the theory meets the ground. Every ton the machine carries, every braking load, every turn, every haul cycle eventually comes back through the contact patch. So when the tire reaches this scale, changing it is no longer a routine shop job. It becomes another controlled lifting task inside the larger maintenance system. The final sequence may be the least glamorous, but in some ways it is the most honest. Washing down a giant mine truck with water cannons, blasters, and high-pressure equipment does not look like the heroic side of industry. But this is where the larger truth settles in. Giant machines stay in service because people keep doing the repetitive, dirty, physically demanding work that inspection and upkeep require. The description of older washwork even mentions hardened buildup falling loose in chunks weighing around 200 pounds. That makes for a powerful ending because it strips away the spectacle without reducing the importance of the work. The giant lift, the major rebuild, the dramatic assembly, and the huge haul truck all depend on routines like this. Cleaning exposes damage, maintenance prevents escalation, inspection catches what scale tends to hide. So this is where the full meaning comes together. The world of extreme lifting is not really about giant cranes for their own sake. It is about the industrial systems those cranes serve. Systems built from oversized machines, sustained by careful rebuilds, protected by maintenance discipline, and kept alive by people doing skilled work long after the dramatic moment is over. And once a tire reaches that kind of scale, replacement is no longer the only economic answer. This retreading machine exists because giant off-the-road tires represent major value. The process shown here includes cementing, filling, building, and pressing. In other words, the tire is not treated as a disposable wear item. It is treated as something worth rebuilding in stages, much like the machines it supports. That is a useful payoff for everything that came before. Extreme industry is not just about first installation. It is about extending the useful life of expensive systems wherever that can be done safely and economically. The same mindset that produces giant cranes also produces giant maintenance workflows.
Then the focus narrows from giant scale to technical discipline. This sequence is smaller in visual drama, but it matters because it shows how this world protects itself from hidden failure. The allowable repair zone is limited to the center crown area, and the maximum repairable injury is only a 1/4 inch. Shoulder and sidewall damage are off limits. That is a tiny number compared with the machines already seen, but that is exactly the point. Heavy industry does not survive on size alone. It survives on limits. Knowing what can be repaired, what cannot, and where a small mistake could become a dangerous failure belongs to the same culture of control that governs major lifts. At this scale, a tiny flaw can still lead to very large consequences.